The Norwegian Public Roads Administration plans to create a coastal highway route that would run between Kristiansand and Trondheim. CNN reports the new highway would include bridges as well as submerged floating tunnels that would connect different fjords. It is expected to cut travel time by half.
Norway is embarking on the largest roadway infrastructure plan in its history. In fact, it may be the largest road revamp in the entire world. With a budget of $47 billion, this new coastal highway is going to connect areas of Norway that used to take 21 hours to travel between.
A tunnel is being constructed 390 meters beneath sea level, and it's deep enough to generate clouds inside. Above it, a bridge spans 5 kilometers across a fjord so deep it can't be anchored to the earth, so engineers made it float. As NBC called it, the world's first floating tunnel proposed in Norway.
Rogfast is the first in a series of crossings that will link the E39, connecting Stavanger and Haugesund via a 27-kilometer, 16-mile undersea tunnel. This structure will reach depths of up to 390 meters below sea level, making it the deepest as well as the longest undersea road tunnel in the world.
This isn't fiction, it's Norway. And these aren't just infrastructure projects. They're answers to questions no one else dares to ask. How do you build a bridge when the sea is too deep to touch? How do you carve a tunnel through bedrock under crushing water pressure? How do you suspend a highway inside the ocean and keep it there? Let's show you the answer. Norway found to these questions, Norway wasn't meant to be connected. Its land was carved by glaciers that didn't care about roads, cities, or people. What they left behind is a masterpiece of destruction, a coastline sliced into thousands of fragments, each one separated by towering mountains and vertical oceans, fjords. From the air, they look majestic. From the ground, they're a civil engineer's nightmare. These fjords aren't just deep, they're chaotic. Depths vary within meters, often reaching 400 to 1,300 meters without warning. Slopes drop almost vertically from the shoreline, leaving no space for onshore abutments or shallow foundations. Beneath the water, the geology is a layered mess. Hard Precambrian rock, twisted with ancient fault lines, overlain by unstable glacial till and marine clay. And yet, people still live on both sides. Industries operate. Children go to school. This country must function. But here's the problem. Traditional infrastructure doesn't stand a chance here. You can't build piers when the seafloor is half a kilometer below the surface. You can't dig tunnels through soft marine sediment without risking catastrophic water ingress. Even suspension bridges, the world's go-to for long spans, fail in this context. Their towers would need to be taller than skyscrapers just to reach the seabed, and their cables would be exposed to constant gale force winds, vortex shedding, and asymmetric loading from storms funneled through narrow fjords ferries. They've long been Norway's lifeline, but they're slow, vulnerable to weather, and in winter, entire routes can shut down. Emergency services, trade routes, and logistics grind to a halt, not because of conflict or corruption, but because the land simply refuses to cooperate. The country had a choice: submit to geography or engineer a new kind of reality. That's when Norway started experimenting. Quietly, carefully. They began testing ideas that no other country dared attempt. Floating bridges, undersea tunnels carved from bedrock, and now, the world's first submerged floating highway, suspended inside the water like a pipe beneath a storm.
The Norwegian Public Roads Administration plans to create a coastal highway route that would run between Kristiansand and Trondheim. CNN reports the new highway would include bridges as well as submerged floating tunnels that would connect different fjords. It is expected to cut travel time by half.
This wasn't a single decision. It was the result of decades of confrontation between engineers and nature nature kept winning until the engineers stopped playing by everyone else's rules. Welcome to the world of pontoon bridges, but not the kind used by armies in wartime. These are permanent, massive, and terrifyingly smart. The most ambitious of them all is the planned Fjord Bridge, which will stretch nearly 5 kilometers across a fjord more than 500 meters deep. Too deep for foundations, too turbulent for fixed towers. So how do you make a bridge like this float and not drift? The answer lies in something called hydrostatic equilibrium, calculated down to the cubic centimeter. The bridge floats on giant hollow concrete pontoons, each one engineered like a ship's hull, designed to displace just enough water to support its weight, plus the weight of traffic, wind, snow, and storm surges.
Fjord, located to the south of Bergen, stands 5 kilometers wide and reaches depths of 600 meters. To cross this challenging stretch of water, a proposal has been put forward for a floating bridge, anchored to the shore at both ends.
But buoyancy isn't enough. The sea isn't still. The bridge has to resist dynamic forces, wind gusts that create like lateral push, waves that add vertical lift, and currents that twist the entire structure like a ribbon. To fight this, engineers tether the bridge using tension leg moorings, cabled deep into the seabed and arranged in a triangulated pattern. These moorings aren't just anchors, they're intelligent stabilizers, absorbing kinetic energy and dampening motion, the same way a suspension system works in a high-performance car. And then there's the curve. Yes, the bridge curves, intentionally, not for aesthetics, but for aerodynamics. In this part of Norway, wind shear from the fjords can reach speeds above 110 kilometers per hour. A straight bridge would become a wind tunnel, amplifying drag and risking overturn. But a curved bridge breaks up the airflow, dispersing pressure and guiding vehicles through with a gentle arc. Inside the bridge itself are systems you'll never see but always depend on. Pressure valves that adjust ballast during heavy rain, flexible expansion joints that shift with the tide, and sensors embedded in the deck to monitor fatigue and load distribution in real time. It's not just a bridge, like it's a floating machine. And this machine has already proven itself. Norway has built several smaller floating bridges already, including the Nordhordland Bridge. And none have failed. Not in decades of storms. But as revolutionary as these bridges are, there's still one limit. They work only when a fjord is wide and relatively calm. What if the fjord is too narrow, windy, or so deep it swallows bridges and moorings? That's when Norway decides to go not over, but under. This is where we meet Rogfast, the tunnel that doesn't just break records, it redefines what a subsea tunnel even is. Once completed, Rogfast will be the longest and deepest undersea road tunnel in the world, 26.7 kilometers long, plunging to a depth of 390 meters below sea level. Not under land, under pressurized seawater, slicing through ancient bedrock in complete defiance of logic. But it's not the scale that makes Rogfast unique. It's the method. In most modern tunnel projects, engineers turn to tunnel boring machines, TBMS. These mechanical worms chew through the earth with surgical precision, laying rings of concrete as they go. But in Rogfast, that method's too slow, too rigid, too dangerous. Instead, engineers here use controlled drill and blast techniques, blasting directly into the Precambrian granite that makes up Norway's lower crust. Why? Because this rock isn't uniform. It's veined, fractured, and water-charged. TBMS can seize up or crack under uneven conditions. Explosives, though. Explosives adapt. Each blast is a sequence. Measure, drill, load, detonate, ventilate, excavate, then repeat. Over and over, carving a path through rock that's been untouched for 1.5 billion years. The risks at this depth are extreme. At 390 meters below sea level, the tunnel must withstand over 4 megapascals of external water pressure, enough to implode poorly sealed sections. So the tunnel isn't just lined, it's armored. First, a layer of steel fiber shotcrete, then a high-pressure waterproof membrane, then a secondary concrete shell. Cast in place, not prefabricated, to account for the tunnel's micro variations, but structure is only half the story. At these depths, even air becomes a challenge. Rogfast requires a high-capacity, multi-directional ventilation system, not just to provide oxygen, but to regulate humidity, temperature, and gas buildup from blasting residue and vehicle emissions. Jet fans spaced every 500 meters push air through the tunnel at variable speeds, dynamically adjusting to traffic density and real-time CO2 readings. Backup diesel generators, embedded in caverns carved parallel to the main tunnel, ensure ventilation never fails, even during a total grid blackout. And if something does go wrong, there are emergency bays every 250 meters, pressurized fire-resistant chambers, thermal cameras, sealed evacuation tunnels with one-way escape doors that can be closed with a hand lever in under 5 seconds. Rogfast isn't just a tunnel. It's a sealed survival system under an ocean of pressure. But even this remarkable feat has limits. Because sometimes the seabed isn't just deep. It's endless, unstable, or simply unreachable. And that's when Norway steps further into the unknown. Into a space where the tunnel doesn't sit in rock or on water. It floats beneath the sea. The concept is known as the Submerged Floating Tunnel (SFT), and if realized, it would be the first of its kind anywhere in the world. A hollow, pressurized tube suspended 20 to 30 meters below the surface, never touching the seabed or protruding above the waves. But this isn't science fiction. This is a mathematically modeled, physically tested, and strategically scoped proposal for one of the most complex marine environments on Earth. Here's how it would work. The SFT consists of twin-lane tunnel tubes, each made of high-density, reinforced concrete, shaped in elongated cylinders with slight curvature to counter internal stress. These tubes are not fixed in place like traditional tunnels. Instead, they're buoyant, engineered to maintain a neutral or slightly positive buoyancy to stay suspended beneath the water's surface. So, how are they held in position? There are two main anchoring strategies. Tethered cables to the seabed. Placed at regular intervals, these cables prevent vertical drift and resist uplift forces from buoyancy and traffic-induced motion surface pontoons with vertical cables. Where seabed anchoring is impossible, floating pontoons on the surface hold the tunnel from above. These pontoons are spaced to allow unimpeded shipping lanes and absorb surface wave forces that would otherwise transmit into the tunnel body. The forces acting on an SFT are complex and constant. Not just buoyancy, but also wave loading, currents, pressure differentials, thermal expansion, and even seismic vibrations from distant tectonic zones. To survive, the tunnel must behave like a living structure. It must flex, self-correct, and absorb rather than resist. Every meter of the tunnel is designed with modular articulation joints to permit motion without fracture. Built-in pressure equalization chambers help maintain internal equilibrium as vehicles pass through. Internal hydraulic dampers act as shock absorbers during sudden pressure spikes, while automated ballast control tanks adjust the tunnel's vertical stability in real time. Even the materials are futuristic. Some prototypes incorporate carbon fiber reinforced concrete, while others explore glass fiber hybrid composites to reduce weight without sacrificing tensile strength. But it's not just about engineering, it's about invisibility. Unlike a bridge or a surface tunnel, an SFT leaves no visual trace. It sits in a silent zone of the water column, far below waves but far above sonar-sensitive marine life. Some defense experts see it as a strategic corridor, a structure that could mask submarine movement, shield coastal assets, or transport troops in complete stealth, all under the guise of civilian infrastructure. It hasn't been built yet, but simulations are underway. Environmental models are being tuned, and full-scale prototypes have passed submersion and anchoring tests in test fjords. The only thing standing between theory and reality? A place too difficult for anything else to work. And that's what Norway has always been looking for. A place where no other option exists. But even innovation has its limits. What happens when even floating inside the ocean isn't viable? Norway found its answer. Not forward, not across, but straight down. In 2018, Norwegian engineers quietly tested something no other country had seriously attempted. A vertical access tunnel drilled straight into the side of a fjord cliff, like an elevator shaft into the underworld. Not a utility duct, not a mine shaft, but the beginning of what could become the world's first vertical descent infrastructure system for public roads. The location: a steep rock face overlooking the Fjord, the deepest fjord in Norway. The goal? To test whether a tunnel could drop vertically into a mountain, then connect with a horizontal passage far below, forming a helical ramp or even an elevator system for vehicles, linking inaccessible terrain without a single horizontal meter on the surface. The experimental shaft reached 40 meters in depth, drilled into solid granitic gneiss known for its hardness, density, and unpredictable fracture propagation. Engineers used diamond-tipped rotary drills to achieve vertical precision within plus or minus 5 millimeters, a necessary tolerance if vertical descent systems are to support future vehicle lift or spiral ramps. To handle potential groundwater ingress, a major risk in vertical tunnels, the shaft was sealed with dual-stage grout injections. These used a combination of polyurethane hydro-expanding compounds and microfine cement, injected under pressures of up to 400 kilopascals. The result? Total leakage was recorded at less than 0.8 liters per hour, even under simulated pressure heads equivalent to 600 meters below sea level. But the real surprise came during thermal shock testing. Norway's fjords experience intense freeze-thaw cycles, sometimes within 24 hours. Engineers subjected the tunnel to controlled temperature swings from negative 15 degrees Celsius to plus 45 degrees Celsius, then monitored the lining for spalling, delamination, or microcracking using acoustic emission sensors. No critical failures were recorded. A vertical tunnel like this isn't just a novelty, it's a geometrical breakthrough. Most tunnel designs rely on horizontal progression, but in places like the fjords, where cliffs rise hundreds of meters and there's no space for horizontal access, vertical shafts unlock a new dimension of design. They could connect a floating tunnel below to a mountain road above, or serve as emergency egress points for submerged systems where horizontal escape routes are impossible. And with spiral ramp engineering improving, inspired by deep mine infrastructure in South Africa and Chile, Norway is positioned to adapt industrial tech for public mobility. There are even concepts for car elevators that could use magnetic levitation to transport vehicles up or down in under 90 seconds, bypassing road switchbacks entirely. What comes next? The Sognefjord test shaft remains unused for now, but its data lives on in the archives of Statens Vegvesen, the Norwegian Public Roads Administration, waiting for the right fjord, the right crisis, or the right leap of necessity. Because in Norway, that's when breakthroughs happen, when there's no other way left from floating bridges to submarine tunnels, from vertical shafts to submerged highways. Norway's solutions aren't just engineering marvels, they're acts of geopolitical independence, cast in concrete and anchored in bedrock. Where others see structure, Norway sees sovereignty. Where others take shortcuts, Norway digs deeper, literally. And that's what makes Norway's infrastructure the most advanced in the world. Not just because of what it connects, but because of who it answers to. Do you think anyone else could do that? Do you want to see more videos like this? If yes, subscribe to our channel and press the bell icon. We bring you exclusive content on groundbreaking projects, technological advancements, and major global developments that no one else is covering. Thanks for watching, and until the next video, stay tuned.